So here I am at Pearson Airport, and if you take a look behind me, it appears to be stationary. Yet if you stare at my feet are moving, and it's rather weird. In fact, if my feet stop moving, the background starts moving. Why is that? Well, let's see why in today's episode.
If you've ever been on a treadmill before, you might have experienced this phenomenon. Even though your feet may be trying to propel you forwards, somehow when you look at the environment, you appear to be stationary. What's really happening is that even though your feet are moving relative to the treadmill belt, the belt is moving in the opposite direction relative to the ground. And since these numbers are equal and opposite of each other, they net to a value of 0. There is a formula used to describe this, and it looks something like this. O is for the object, M is for the medium, but you can think about it as a material, whether it may be the air, water, or in this case over here the treadmill belt. And lastly, G is for the ground or the surrounding environment. One thing to keep in mind is that in order for this formula to be valid and true, adjacent subscript letters must be the same. You'll also notice that the leftover letters are used to describe the picture at the end of the day. Let's try out another example that's a bit more interesting. Let's say you are standing on top of a ball. Or let's say you're moving relative to the ball. So you are the person, here is the ball. The ball is rolling on top of the cab of a truck, and the truck is driving on top of a big ship. Now the ship is sailing on top of water, and if you look nearby, there's an island. In other words, there's the ground. And you're wondering, what is the velocity of the person relative to the ground? How would you solve that? Well, that's based upon a lot of other relative velocities. First off, you need to know the velocity of the person relative to the ball. Next, you need to find out the velocity of the ball relative to the truck. Then you need to know the velocity of the truck relative to the ship, the velocity of the ship relative to the water, and lastly, the velocity of the water relative to the ground. In the setup over here, you can see that we're still abiding by that rule. Adjacent subscript letters are the same, and whatever letters that are left over at the end, that's used to describe the overall picture, the velocity of the person relative to the ground. Here's a two-dimensional problem. Let's say you're trying to sail directly south, and you're able to paddle at 3 meters per second. On this particular day, the river current is drawing you towards the east at 4 meters per second. Consequently, you end up sailing in this diagonal path. To solve for that diagonal angle, what you need to do is that you need to connect these two vectors from head to tail and draw your resultant vector pointing to the head of the last vector drawn. Luckily, in this case over here, it creates a right angle triangle, so we could use the Pythagorean theorem in solving it. But before we get there, let's break everything down into its horizontal and vertical components. So we'll take the formula VBG is equal to VBW plus VWG, and yes, you could use different letters. In this case over here, B is for the boat and W is for the water. First off, make sure that adjacent subscript letters are the same, and the leftover letters are used to describe the big overall picture. And now you can solve the problem by its components. Now horizontally, only the river current is carrying you towards the east. And vertically, you're the only factor that's moving towards the south. We can use the Pythagorean theorem in solving it. Now this one looks rather complicated, but we can simplify it by simply erasing the arrows. Once you remove the arrows, it becomes a scalar quantity anyways. We can then sub in all the values and get to our final answer. To solve for the corresponding angle that we're sailing in, we notice that we have the opposite side and the adjacent side, and that's why we're going to do tan inverse. The tan inverse of 4 over 3 gives you 53 degrees. To get the final mark, you need to state the final conclusion. The velocity of the boat relative to the ground is traveling at 5 meters per second, south, 53 degrees towards the east. Here's a scalene triangle example. A boy is trying to throw a ball directly towards the west. However, on this day, the wind carries the ball and blows it towards the northeast. As a result, the ball doesn't end up traveling west. Instead, it ends up traveling in the direction of this green vector. Before we move forwards, we want to check two things. First, is the formula correct? Yes, wind is adjacent to each other in subscript, and the leftover letters describe the overall picture that we're trying to solve. Next, we're going to compare the formula with the diagram. Are we adding VBW with VWG and connecting them from head to tail? Yes. Is that used to describe our resultant vector? Yes. So that's perfectly fine. Now we can solve this problem by using either the trig method or the component method. In this example, we'll solve using the component method. If we're trying to solve for VBG, we need to first solve for our horizontal component of VBW and subtract it with the horizontal component of VWG. VBW is already traveling in the horizontal dimension, so we don't need to use sine or cosine. But for VWG, we probably do need to use it. Since we know that this vector over here is opposite of 15 degrees, we're going to multiply the hypotenuse by the sine of 15 degrees. So 40.2 subtract 2.68 times the sine of 15 will give us 39.51 meters per second towards the west. As for the vertical dimension, since VW doesn't have a vertical component, that's why that term goes to 0. And as for the wind, this blue vector is beside 15 degrees, and that's why we're going to multiply by the cosine of 15. Now that we have the horizontal and vertical components, we can solve for the hypotenuse by using the Pythagorean theorem as well as tan inverse. State your final answer, and you're good to go. Now, the most challenging of problems is the one where you're not given the entire story. You're given pieces of it. For example, let's say a boy decides to throw a snowball and he wants it to reach at a destination somewhere towards north 74 degrees west. Alright, so the boy is all the way down here and he's trying to throw a snowball to hit a snowman somewhere over here. Now, if he tried to throw it in this given direction, the wind will blow the snowball towards the north, and unfortunately it's not going to reach his target. So the only way for the boy to throw the snowball and for it to reach the snowman, he needs to throw the snowball slightly towards the south. So he's going to throw the snowball in this direction over here to be carried by the wind, so at the end of the day it will go in this path here. Before we move forward, we need to do the two big checks. First, we need to make sure that the formula is correct. The adjacent subscript letters are the same, and that the leftover letters describe your overall picture. Next, we need to make sure that the formula matches up with the diagram. We need to check and make sure that vector 1 is connected to vector 2 from head to tail, and that the resultant vector points to the head of the last vector drawn. Everything looks good. Now we can continue solving the problem. Currently, we don't know two of these angles. The angle down here and the angle over here. And that's because we don't know the angle of VBW. So let's try to see if we can solve for this angle all the way up here. And it is possible. For one thing, we know that the angle over here is north 15 degrees towards the east. And if we draw a vertical line over here, we can use the Z pattern and discover that the angle over here is also 15 degrees. There's also another Z pattern in this picture, which is this large Z over here. If it's 74 degrees over here, then in this little corner over here, it is also 74 degrees. Meaning that if we add the 15 with 74, yes, we can solve for this corresponding angle, and we'll call it angle C. Anytime you have an angle and a corresponding side length, which we do have, we can solve using sine law. Angle B is of no use to us right now, so we're going to solve for angle A, and that's why we're going to use sine of A over A is equal to sine of C over C. We isolate for angle A, sub all the values in, and we'll get an answer. Now this 3.82 degrees is used to describe this smaller angle over here. we want to figure out how he must direct his ball relative to north. So we're going to take 74 degrees and add 3.82 to it. What this tells us is that Calvin needs to pull out his compass, direct the ball at north 78 degrees towards the west, and when he throws the snowball, the wind will carry the snowball towards the north, and eventually he'll hit X marks the spot.